The great civilizations of the past laid the foundations for our modern world. The Egyptians, the Greeks, and the Romans are all rightly celebrated as brilliant innovators. But the history books have overlooked a magnificent period of invention when some of the greatest minds of antiquity revolutionized scientific and technological knowledge. This is the marvelous story of the machines of the East. To many Westerners, the Islamic East is shrouded in mystery, and its history is obscure. But today we are discovering that the technology and science that shapes our modern world has its roots in a remarkable civilization that originated and spread throughout the East over 1,000 years ago. Incredibly, those people had ancient handheld computers that possessed many of the capabilities of modern satellite navigation systems. They created massive water-moving machines that harnessed the power of the earth to transform deserts into rich and vibrant cities. They understood the complex precision engineering that underlies the components fundamental to many contemporary machines. And they invented awe-inspiring combat devices, including fireproof uniforms and even the world's first torpedo, capable of destroying a ship 300 meters away. For the history of Western civilization, the collapse of the Roman Empire was a decisive turning point. Whereas Europe slid into the Dark Ages, abandoning many of the advances of the great cultures of antiquity, the lands of the East flourished. In the void following the end of the ancient empires, important developments in literature, natural science, mathematics, medicine, and engineering took place. What occurred in a sparkling 500-year period between the 8th and the 13th centuries, known as the Golden Age of Islamic civilization, is now making us rethink our views about the ancient world.
Many of the scholars, engineers, craftsmen were amazingly innovative, and it was at a time of great creativity.
As Islamic culture spread from the Middle East to India, North Africa, and westward across Europe as far as Spain, the scholars of the East amassed the greatest collection of knowledge in the world. Over the following 5 centuries, the lands of the East became the planet's vibrant heart of scholarship and culture.
Europe couldn't have possibly reached where it did without the contributions of these people.
From the period, call it from 700 right further up to 1600 and beyond that, because it never stopped. It was a world of learning.
By the end of the 8th century, one school of learning in particular led the way in technological and scientific development. It was known as the House of Wisdom, the Islamic world's equivalent of MIT or Oxford. It attracted scholars from all over the East. They decoded ancient texts that contained designs and specifications for machines that had existed over 1,000 years earlier.
Early Arabic inventors took many of these Hellenistic and Roman writings, copied them, but also added and elaborated and developed some of these principles further.
Intriguing hints in some manuscripts indicate that Eastern engineers inherited a tradition of constructing automata, the ancient world's equivalent of robotic devices. Contemporary engineers, like Professor Al-Hassani of Manchester University, are now studying automata like the tea-serving girl, and are astonished by the fluent understanding of techniques that we still employ today.
The tea-serving girl principally is a tank on top of a robot. This tank has a hole that allows the water or the drink or the tea to come out of it.
A tank that ingeniously regulated the flow of liquid enabled the creator of the tea-serving girl to astonish and amuse all who saw her. The reservoir is filled with liquid, which drips at a constant rate into a bucket. When the liquid reaches a certain level, after precisely 7.5 minutes, it empties into the glass in the servant girl's hand. The weight of the glass triggers a mechanism that causes the girl to roll down a slope, opening the door and presenting the drink to the guests. This kind of trick device would have further enhanced the reputation for genius and mystery that surrounded the engineers of the time. From examination of the antique texts and archaeological remains, we're now learning that Eastern engineers may have been responsible for unlocking the secrets of the world's very first computer. At the start of the 20th century, the discovery of a shipwreck off the Greek island of Antikythera yielded ancient history's most enigmatic scientific object. Made in 80 BC approximately, scientists believe that this may have been an early form of analog computer. It is called the Antikythera mechanism. It has gears which have prompted scientists to re-evaluate their ideas about technology in the ancient world. However, despite being studied by some of the finest minds around, exactly how it worked remains a mystery. Are there any clues in the known Islamic texts that might tell us how it operated? A design for an 8-geared calendar dating from the 10th century AD has been found in a manuscript attributed to a scientist and astronomer known as Al-Biruni. Al-Biruni's machine harnessed the power of geared technology to track the movements of the solar system. Consisting of 8 bronze gear wheels that incorporate over 200 teeth, the machine was an outstanding technological achievement. All the displays were set to their correct astrological positions before the machine was operated. Each day, the user moved the alidad, or pointer, forward 1 division, so turning the gears, which gradually altered the positions of the sun and moon, and the shape of the moon in its phases. The fine precision of the bronze-toothed gears ensured the machine was amazingly accurate in calculating days, months, and years. Could the Eastern scholars have been aware of the Antikythera mechanism, and did they possess the skills to build instruments like it? In a book written in the 16th century by the scientist Taqi al-Din is a description of a machine that scholars think is a sophisticated water-lifting device. The remarkable 6-cylinder monoblock pump driven by water power employs what appears to our eyes to be 20th century technology and looks like a machine invented just recently. In Dubai, model makers have reconstructed this complex piece of equipment.
This machine is the 6-cylinder pump from Taqi al-Din. It's a water pump. It's driven by a grand water wheel. The water wheel is actually linked to an axis, or camshaft. The camshaft has 6 different cams on it. Each rod is linked at the end of the point with a weighted ball.
Opposite each cam is a lever arm supported in the middle and pin-jointed at the other end to a vertical piston rod. The upper end of each piston rod carries a lead weight. The bottom of each piston cylinder has a clack valve. When the water wheel rotates, each lever arm is raised in succession by the cams. Water is then drawn up by the piston through the valve. When the lever is released, the lead weight propels the water up through the delivery system.
It's a wonderful evolution from the Mana Musa brothers in the early 9th century, further down to where Al-Jazari was a fantastic ingenious engineer until Taqi al-Din for that particular era.
So it was not only ingenious scientific objects and instruments that were built in the Islamic world. The inventors also created fully automatic mega machines designed to ensure the survival of millions of people using technology not seen again for 500 years. By the 13th century, the inventors of the East had become the world leaders in developing new concepts in technology. The machines created during the golden age of Eastern civilization were designed to demonstrate ideas that were both complex and revolutionary. There is one inventor who stands as a colossus in the annals of technology. However, his remarkable legacy is virtually unknown in the West. His name is Al-Jazari, and he wrote the definitive treatise on Eastern Islamic engineering. The text is known as the Book of Knowledge of Ingenious Mechanical Devices. So important is this work that without it, 500 years of Eastern technological progress would be unknown to us. In the Topkapi Museum in Istanbul, Turkey, there is a rare copy of Al-Jazari's manuscript. It was written in 1206 AD and contains within it blueprints of many of the components that are crucial to modern engineering.
Al-Jazari, as his name says, comes from northern Iraq in the late 12th and the early 13th century. He was a very gifted engineer.
Al-Jazari's world incorporated some of the hottest lands on Earth, and he would have been acutely aware of how essential water was to sustaining its people and its culture. He created a series of machines, each of which would help society not only survive, but thrive in the sometimes dangerously arid climate. Al-Jazari made huge advances in the development of mechanical technology in order to design his water-raising devices. What is fantastic is that many of his machines match the principles of today's devices exactly.
He tried to take age-old standard technology for lifting water, for irrigation, and tried to improve them.
Devices for raising water like the shaduf generally relied on animal or manpower to drive them. Al-Jazari removed the necessity for human, ox or horsepower by designing a set of fully automatic lifting machines that used the power of the water itself to drive the mechanisms. One of the most intriguing has become known as water-raising device number 3. Until recently, it was thought that this complicated machine was an unrealized idea of Al-Jazari's that existed only as a concept. But in Damascus in Syria, a water wheel on the river Yazid seems to be actually based on Al-Jazari's design number 3. It offers us a fascinating glimpse of his genius.
Al-Jazari was really a gifted practitioner. He was not only writing in his tradition, but he was really building them.
From its inauguration in the 13th century, this water wheel served the local community for over 700 years. Incredibly, it was still transporting water to a nearby hospital until the 1970s. Al-Jazari was a man who would often revisit and improve his designs. This astonishingly complete example is based on his third design for a water-raising device and uses the intricate system of gears that is common throughout his work.
In his book, Al-Jazari mentions that this water-lifting device is designed to work by means of scoopers. That is, water falls down on the scoopers from a certain height, causing them to rotate. This, in turn, drives the pinions and axles which move the water-lifting buckets. This device has the same engineering principles, but rather than water falling, it works by horizontal water power in the Yazid River.
The water wheel was moved by horizontal boards, which caused rotation that drove gears, pinions and axles to lift the water upwards. It was raised over 10 meters to the top of the tower.
Up here, there are 3 wooden parts which have survived intact. A horizontal cogwheel was linked to a vertical cogwheel, which transfers the movement to a pulley where a set of chains and buckets is installed.
The buckets carried water from the river to the top of the tower, from where it was discharged into an aqueduct to flow gently downward to the hospital. The wonderfully well-preserved device is a fine example of the use of technology to improve the quality of life for the people. But it was Al-Jazari's design for his 4th water-raising machine that would take the technology a vital step further and change mechanical engineering forever. It used a crank system. This is the earliest known use of this technology in a working machine. The crank is considered by today's engineers to be the most important single mechanical device after the wheel. What makes this invention so extraordinary is that 500 years later, it would play a significant part in ushering in the modern era.
The use of the crank and connecting it to what we call a camshaft, this had revolutionized machinery and engines like the steam engines and the diesel engines and the petrol engines.
This simple mechanical component allows the conversion of continuous rotary motion into a reciprocating one. Hand-operated cranks had been understood for centuries, but the incorporation of a crank-connecting rod system in a rotating machine represented a huge advance. Contemporary engineers who have studied Al-Jazari's design have observed that the horizontal axle of the machine is turned by gears, and that the end of the crank slides in the hinged connecting rod, causing it to oscillate around its hinge, thus making the water bucket rise and fall. Until scholars deciphered Al-Jazari's design, it was believed that this system was the invention of 15th century Europeans. But in fact, Al-Jazari was using this crank device in his machine 2 centuries earlier. There are several other large water-moving devices in existence, which show how widespread sophisticated technology had become throughout the region. One of the most efficient types of a fully automated water wheel is called a noria. Many survive to this day. The best preserved examples are located on the river Orontes near Hama in Syria. Described by the Roman engineer Vitruvius, writing in the 1st century BC, the noria is a superbly simple water-lifting machine.
The beauty of the noria is that it runs unattended, it's automatic, it uses natural forces to do the work for you.
These powerhouses have been calculated to raise up to 95 litres of water per minute. They offer us a fascinating insight into much earlier norias found all across the East.
It's a water-driven wheel with compartments or buckets on the rim and paddles on the outside of the rim. The wheel is driven by water flowing underneath, and as the wheel goes round, compartments dip underneath the water, water enters through a hole in the leading edge, the compartment's carried up to the top of the wheel, and the water discharges into a trough or launder near the top of the wheel.
The diameter of the largest wheel was about 20 meters, and there were 120 water collection compartments in the rim. The brilliant designs of Al-Jazari and the beautiful surviving examples of water wheels in the East are tantalizing evidence of the sophistication of the technology available in the medieval Islamic world. But there are other surviving mechanical devices that are so advanced, scholars were, until recently, unwilling to accept that they were not created from 21st century technology. The machines of the East extended technological advances made over many centuries. In the ancient world, Greek and Roman engineers made enormous progress in mechanical engineering. Inventors like Heron of Alexandria and Philon of Byzantium were major influences on Eastern minds 1,000 years later. Scholars who are now translating Arabic texts are beginning to uncover evidence that shows that we haven't invented modern machines. We've merely rediscovered them. What we are finding out is causing us to rethink the history of mechanical engineering, from the Greeks and before, through to the work of Renaissance inventors like Leonardo da Vinci.
I'm quite convinced that the modern world would have developed in a very, very different way if Islamic civilization had never arisen.
We know that one Islamic inventor in particular would change technology forever. Al-Jazari's final design for a water-lifting device contained an amazing mechanism seen for the very first time in history. Many people think that the double-action suction pump was invented in the 20th century. In fact, it's over 700 years old. Al-Jazari himself looked to his ancestors for inspiration. Eusebius, working in the city of Alexandria in Egypt about the 3rd century BC, began to formulate the principles of the suction pump. In the Technology Museum at Thessaloniki in Greece, engineers have constructed Eusebius's pump using antique manuscripts as their guide. Unbelievably, this 2,000-year-old design can still be found in use today in the fields of Northern Europe.
Here we have Eusebius water pump. It's called a two-stroke water pump. It consists of 2 cylinders, each containing 1 piston and having at its bottom a valve, a water valve. The pistons are moving by the use of these handles here. As each piston moves upwards, it empties the cylinder from air, and its place, the air's place, is taken by water. The pistons are moving in opposite directions, ensuring that we have a constant flow of water. It was used from the ancient times till nowadays as a water pump, but we can say that it's the ancestor of a two-stroke engine, a motor engine that we use today, because if we replace water with a mixture of gas and air, we have the same principle in operation.
1,000 years later, Al-Jazari would take the essential structure of Eusebius's design and take it to new heights. While his machine relied upon human muscle to pump water, Al-Jazari applied mechanical knowledge to make a pump that was automatic. This would have a direct influence on the history of engineering, and along with his crank system, would be in general use 500 years before the invention of the steam engine.
Take Jazari's machine number 5. It is actually a double-acting suction pump. It has got 2 cylinders with pistons reciprocating to the right and to the left.
The pump is driven by a water wheel which propels through a system of gears an oscillating slot rod to which the rods of the 2 pistons are attached. The pistons work in horizontally opposed cylinders, each provided with valve-operated suction and delivery pipes. The delivery pipes are joined above the center of the machine to form a single outlet into the irrigation system. Al-Jazari's developments in the construction of water-moving machines encouraged other Islamic scientists to refine the technology and construct ever more elaborate devices. While Europe lagged behind in technology during this period, engineering in the East became even more advanced than we had previously thought.
There was a really vibrant tradition of mechanical science in the early Islamic world, in total contrast to Western Europe of the 7th to 9th centuries.
3 brothers born around 800 AD pioneered the techniques of engineering significantly. They were collectively known as the Banu Musa brothers. Inspired by the translations into Arabic of the ancient inventors Philon and Heron, they created an array of machines that advanced the work of their predecessors in many respects.
The science of mechanics was generally known as the science of tricks, because what one is doing, one is using mechanical phenomena to actually achieve what could have been impossible to achieve.
The key was the sophisticated application of hydraulic principles. By controlling air and water pressure, the Banu Musa brothers were able to regulate their machines automatically. The precision engineering techniques employed in this trick device would lay down many of the tenets of modern mechanics.
This typical machine is effectively to give you an intermittent spouts of water or a drink. It uses very cleverly 2 new systems which were introduced in the early 9th century.
The first is a conical ground valve, which is used to regulate the flow of water.
When the water is in the top tank, it will go through a hole in the bottom of the tank, like it is now doing there. In that hole, there is a conical ground valve that if it goes up, it would shut the hole.
The second is a feedback mechanism that controls the timing of the movement of the valve.
Because there is a siphon system in the middle tank, it will suck the water back into a smaller tank below. Now, the third lower tank has a float. If the float goes up, then water will gush out. However, because it goes up, it will push that seating valve because it's connected with the seating valve, and then it will stop the water coming down from the top tank.
This device and others like it demonstrate an advanced knowledge of the functioning of differential pressures. Exactly the same techniques are used today to control mechanisms in everything from washing machines to jet engines.
We have seen an emergence of a civilization which has influenced our present-day civilization enormously in our homes, in our hospitals, in our schools. And even when you look up the sky, a lot of the stars are still named by Arabic names.
In addition to hydraulics, we have substantial evidence that the peoples of antiquity also knew how to accurately calculate the movements of the Earth, Moon, and planets. This was vital for navigation, religious observances, and the comprehension of the passage of time. One instrument, which first appeared in Hellenistic Greece around the 2nd century BC, reigned supreme for over 1,500 years. It is the star holder, or astrolabe. The Museum of the History of Science in Oxford contains the largest and most important collection of astrolabes in the world. The curator is Dr. Stephen Johnston.
An astrolabe has been called an ancient pocket computer. Its primary use is in telling the time working with the sun and stars, so it comes from astronomy. It can tell you when the sun rises, when the sun sets, for any day of the year, wherever you happen to be.
The scholars of the East developed and improved the astrolabe's capabilities.
In the 8th, the 9th, the 10th centuries in the Eastern world, the instrument was developed, new variants were devised which were more powerful, which could be used not just in one place or a small selection of latitudes in the world, but could be used universally.
The portability and accuracy of the astrolabe made it something like the BlackBerry of its time.
This is the oldest astrolabe in the museum's collection, dates from the late 9th century, but it's more than just a calculating device. If I turn it round to the back, this is an observing instrument. And if I hold it up, you see how this was used to measure the height of the sun and the stars. I'd adjust that ruler until I was looking through and seeing the star through the little pinhole sights that there are here. Then when I've done that, I read off from the pointer the degrees. There's a scale of degrees going around the edge. That tells me how high something is in the sky. When I've got that, whether it's the sun or a star, I can get the time.
The inventors of the East had become masters of mechanical engineering. Eastern cities were the powerhouses of technological innovation. Inventors like Al-Jazari focused their attention on even more intricate challenges. Using the knowledge they had amassed, they began to create complex mechanical clocks and amazingly effective machines of war. The inventors and scientists of the Islamic East developed technologies that still exercise a major impact on our lives. The greatest of them, Al-Jazari, in his 13th century treatise, The Book of Knowledge of Ingenious Mechanical Devices, codified the mechanical principles that would take us into the modern era. This text is one of the most important records of engineering development of any period in history. It contains designs for more than 50 machines, each described in meticulous detail, in order that other engineers could use them as blueprints and replicate these complex devices. We challenged a leading British model maker, Richard Windley, to recreate one of Al-Jazari's automated machines, a device which used a candle to calibrate the passage of time.
He even laid down the materials the candle should be made from, the precise dimensions of the candle, and even the materials that the wick of the candle should be made from.
Al-Jazari describes 4 candle clocks in his treatise, the most sophisticated in existence.
It works on the basis of a candle slowly burning and altering through a series of pulleys and cords a dial from which the time could be read off. The Islamic day was divided up unequally. The daylight hours and the nighttime hours were different, so that made the whole system even more complicated.
But Al-Jazari's solution was deceptively simple.
And what we've basically got is the candle burning away, being pushed upwards. As the wax melts and burns away, the candle gradually rises. This lead weight is going to descend like so, and in the process pulls this cord here, which passes over a pulley and round an axle shaft. This is the shaft that's connected to the pointer on the dial from which the time can be read off.
This splendid example of a small-scale precision timekeeping device also uses a simple mechanism found in most households today.
It's fairly important that there's some sort of device to hold the cap against the pressure of the weight underneath. And what Jazari did was to use a little kind of L-shaped clip system. And in fact, this is almost identical to what we have nowadays in the electric light bulb, what we now call a bayonet fitting. It's curious that after sort of 1800 years, we're still using an intrinsically similar device.
But there's more. One of the most detailed sections in Al-Jazari's treatise is dedicated to water clocks that demonstrate the enduring principles of hydraulics. In these pages, he describes some of the most elaborate mechanical devices for measuring time ever. One in particular represents an outstanding technological achievement that can still pose a challenge for today's reconstructors. Today, It is called the elephant clock. In the Ibn Battuta Mall in Dubai, MTE Studios have made a large-scale working replica of Al-Jazari's masterpiece. Over 150 experts worked on this 7-meter-high, 7-ton mega clock. It was a massive undertaking that required over 11,000 man-hours to complete. Ludo Verheyen is the director of the Al-Jazari Elephant Clock Reconstruction Project.
This project was quite a challenge because indeed it was the first time that these features have been reconstructed ever. It is complicated. The inventor from 800 years ago, Al-Jazari, was a great inventor, so to learn from his manuscripts in a very accurate way how the mechanics actually worked is quite fabulous.
But how does this magnificent object actually work? And how did Al-Jazari improve so emphatically on the timing devices of his ancestors? Amazingly, the elephant clock consists of several mechanisms that match those used in modern engineering quite closely. Inside the belly of the elephant is a submersible float with a small hole in it. It's calibrated to produce a specific flow of water. This determines the rate at which the float sinks and therefore the time at which the clock strikes. Submergence of the float activates a trip mechanism, which sets a series of events in motion that mark the passage of time and strike the hour. At this point, the float is tilted out of the water, emptying its contents. It then rests on the surface of the water and the cycle is repeated. The clock employs automata, such as a chiming cymbal and a chirping bird, to mark the passing of the hours.
For its time, it is a very complicated clock in the sense that it has automatic feedback, and this continues almost like a perpetual motion machine.
The elephant clock is one of the finest examples of advanced technology from the golden age of Eastern civilization.
So it's a unique combination of art and architecture and also engineering.
The engineers of the East made huge progress in developing technologies that built on the innovations of previous civilizations. But their great minds were also responsible for the creation of ingenious, terrifying weapons of war. They used a form of highly refined gunpowder. It was manufactured to a formula that used common ingredients which were in plentiful supply, including willow charcoal and saltpeter.
By combining them, you turn relatively innocuous components into the driving force of warfare for nearly 1,000 years.
Gunpowder was invented in China, but in its early stages the compound was not explosive enough to be lethal on the battlefield. New evidence suggests that the scientists of the East devised a more potent formula that could be deployed with deadly effect.
It's not until the 12th century, 13th century, when we start to get the mixtures refined to such a way as you can effectively drive rockets, torpedoes, cannons, handguns, and everything we're familiar with ever since. But it was Hassan al-Rama who was the man who really put it down in writing and made it clear.
In the 13th century, Hassan al-Rama wrote a book on military technology that included recipes for gunpowder. So profound was his knowledge, we may have to re-examine our understanding of the history of warfare. In his work, Hassan al-Rama documents what is believed by some to be the first rocket in history, designed specifically for combat.
He lists 22 different recipes for the powder for rockets and different forms of rocket. He's really the father of rocketry.
In the same period, military engineers also built another weapon that harnessed the explosive property of gunpowder, the cannon.
In Spain and North Africa, at the end of the 14th century, there were people who were using the purified and crystallized form of saltpeter in a container, if you will, which was then lit as an explosive to project a small ball. And we have evidence for this from as early as 1377.
There are surviving images of troops carrying such cannon. In one early text from the St. Petersburg collection, known as the Book of Sciences, a description is given of a soldier who carries a midfa, or cannon. It looks much like the standard handheld rocket launcher of today.
Now, in the St. Petersburg manuscript that describes the uses serious and for entertainment, as the title says, of gunpowder, we see pictures of a small barrel on the end of a stick. This is a hand cannon, or even the forerunner of a hand gun. This is the basis of the weapons that are carried by every soldier today.
But the manuscript contains even more amazing evidence of the sophistication of warfare in the Eastern world, the use of fireproof protective clothing.
This is reconstructed based on the St. Petersburg manuscript. We start out underneath with silk tunic. We know that silk's fireproof. Even today, Formula One racing drivers wear silk underneath their Nomex fire suits. On top of that, we've a quilted garment. To a Western warrior of the time, it'd be known as an akaton. That comes from the Arabic al-kutun, meaning stuffed with cotton. But the key part is this on top, which is a woolen overtunic, a fireproof, indeed chemical-proof layer, similar to the nuclear biological warfare suits that a modern soldier would wear on the battlefield.
The manuscript shows warriors with incendiary devices fastened to their clothes. A firestorm would have been created as they were ignited just before the warriors charged into the ranks of enemy cavalry.
The incendiary charges are something like this. They describe linen fibre. This is linen fibre, flax, just a twist of that linen fibre, and in here, a nice bundle of gunpowder, black powder. These are shown on the illustrations of the manuscript, fastened to the fireproof clothing. It also says how they're fastened together with wire. This wire holds the linen fibre, but also allows it to be pushed and fastened onto the garment.
But how effective would this form of protection have actually been? Using the original materials, we put it to the test.
Of course, there'd be literally hundreds of these going off on different men. That would be really distracting to the horses. But for me, the most interesting thing is not even a scorch mark. In fact, it's hardly even warm inside. Fireproof clothing really does seem to work.
One device only recently examined in the Islamic texts has caused us to revisit our ideas about concepts of warfare in the Eastern world.
There are some interesting comparisons to make between these medieval military technologies and much more modern ones. One that particularly comes to mind is the design for what we might call a torpedo.
It was called the egg which moves itself and burns, and it is now thought that this weapon was the first torpedo in history.
It's an anti-shipping device. Unlike a modern torpedo, it didn't slide along under the surface, it skimmed along the surface.
But did Eastern military engineers possess the skill and knowledge required to construct such a weapon?
Until recently, we believed that the torpedo was a 19th century invention. So to learn about a precursor to this from 700 years ago really causes us to sit back and look again at history, particularly the history of naval warfare. This is a torpedo. How effective it is, we don't really know.
To try and find out, we challenged model maker Richard Windley to test this marvel of medieval technology using a design based upon the 13th century original.
The model I've here has been constructed based on illustrations from one of the early Islamic texts from around about 1220. The text talks about a pear-shaped device, or a flattened pear-shaped device. This is made out of copper and iron plate. The main tube running across the top of the vessel is the holder for the black powder charge. The point was so that if it hit a wooden vessel like a ship, it would impale itself and make the removal fairly hazardous. Basically, when we're talking about a rocket, what we're talking about is a cylinder which is filled with compressed gunpowder. These are very similar to fireworks that we use today, and in fact similar to fireworks that the Chinese were making hundreds and hundreds of years ago. This one I've used a sort of fairly novel construction underneath, but it probably would have been hammered iron to produce this kind of flotation vessel.
This would have been filled with an incendiary mixture. Used as a weapon of attack, the torpedo would surely have had a devastating effect on enemy sailors. But could it really have done much damage to the ships?
What we think may happen is that as it picks up speed, it may kind of aquaplane, so it'll probably rise out of the water as it gathers momentum. The two long rods either side are for stability, so they're acting as a kind of rudder. It also keeps the device in a stable attitude in the water. We're using a conventional fuse. It's simply a cotton thread soaked in gunpowder and then dried out. It's what's known as a delay fuse, so we've got just over a second per inch. It's brilliant. That was absolutely amazing. These guys were perfectly capable of making fairly formidable weaponry.
Although we may prefer to believe that after the fall of the Roman Empire, technology disappeared into the Dark Ages, we would be wrong in thinking so. New insights from historians have revealed that the lands of the East inherited and furthered the development of science and technology to new and formidable heights.
I think they were almost more free-thinking in terms of technology certainly than the Romans, maybe even more than the ancient Greeks.
In the years to come, as more Arabic manuscripts are studied, we will undoubtedly uncover more awe-inspiring machines, and we'll have to reconsider who were the great technological innovators that have shaped our world. As new knowledge will inspire us to rewrite the history books, we may have to admit that we didn't invent the mechanized world. We merely rediscovered it.